Greetings and welcome. We're talking today about the second portion of our chapter, probability. And probability and odds specifically, which are different. I think oftentimes these can be used somewhat synonymously in our culture, but inaccurately nonetheless. So here I've got kind of our startup little of our definition of probability of success and failure. Now, what I mean by success or failure is merely from the perspective of the way the event has been described to us. Success is not necessarily innately a good thing, and failure is not innately a bad thing, right? Success might just be, if I'm asking what the probability of getting a tails when flipping a coin, it doesn't necessarily mean that getting a heads is bad. It's just the failure of that event to occur. So if an event can succeed in S many ways, right, and fail in F many ways, then the probability of success, P of S, and the probability of failure, P of F, are as follows. So the probability of success is defined as the number of successful ways the event can occur over the total number of ways the event can occur. And I'll also define that this way, S over S plus F. Because an event can only succeed or fail, it can't do some third possibility. So that's the probability of success. The probability of failure, P of F, would be the number of ways an event could fail over the total number of ways that the event could occur. And more specifically, that would be F over S plus F. Right? So those are the possible ways that that could happen. Right? And probability specifically is a measurement of the likelihood of an outcome occurring. All right? And probability is always going to be a number. Let's see, I'll write it this way. 0 is less than or equal to the probability of an event is less than or equal to 1. All right, so probability is a number between 0 and 1. So you can't succeed 110% of the time, just 100% of the time. Also, I want to point out that P of S plus P of F is equal to 1, right? If I add up all of my the probability of success and the probability of failure, that's equal to 100% of all of the possible outcomes for that situation. So that's kind of a general outline of this. Also, if the probability of an event is 0, that means it is certain to fail or not happen. If the probability of an event is 1, that means it is certain to occur. All right, so for instance, if today is Monday, the probability of event being tomorrow being Tuesday is 100%. It's not suddenly going to skip a day of the week magically. I don't know. So let's do an example here. So what is the probability of rolling a 7 on a 20-sided die? I'll just write that as D20. Bam. Using my, maybe even one D20. What? Classic. So, what's the chance, or the probability, the likelihood, that if I roll a 20-sided die once, that I get a 7? So, let's first figure out what S and F are. So let's see. How many ways can I successfully get a 7 on a 20-sided die? How many 7s are there? One of them. All right. How many not 7s are there? 19 not 7s, right? So the probability of 7 in this situation would be the number of successful ways the event could occur over the total number of ways. So I could write that as 20. Or I could write that as the number of successes plus failures. So 1 plus 19, which I think you guys would agree is still 1 out of 20. And probability often will be written as a fraction, right? but it, however, also can be written as a decimal, 0.05, or sometimes even as a percent, so 5%. 5% chance that that is likely to occur. Now let me define odds for you real quick, and we'll analyze this same problem. So the odds of an event, all right, of success, is a ratio of success to failure. All right, so it is not the likelihood that an event occurs, but it's the ratio of the number of ways the event could occur to the number of ways the event could fail. I believe it also happens to work out this way, that if you knew the probability of success and the probability of failure, you could just divide those two, and that would still give you the same ratio. Because the numerator for success was S, and the numerator for failures was F, and their denominators were the same, so if I divided these two things, the denominators would have just canceled out. I'd still get S over F. So let's talk about odds of the same event occurring. So odds of 7 in this case, well, let's see, how many ways can I get a 7? 1. How many ways can I not get a 7? 19. So the odds is a 1 to 19 ratio, and that's actually sometimes another way you might write it is 1:19. It's not the time. You might also write it a 1:19. All right. And oftentimes odds where you'll see that is in reference to gambling, where it'll kind of determine how they divvy up, you know, the money from a pot or a pool after people bet, and figure out, you know, if you bet on a horse that had like 19 to 1 odds, you probably don't get as much money, whereas if you bet on a horse that had 1 to 19 odds and 1, you end up getting a lot, where 19 people's money ends up going to you, something to that effect. So the likelihood of that is taken into account. Let's see, what is the probability of failure for this 7? Probability of not 7, this little squiggly sign, a tilde, I guess, is what that sign is. Oftentimes in logic is used as a symbol for not, so not is what I'm implying by that. So probability of not 7. How many ways can I not have a 7? 19 out of the total number of ways is 20. So that would be like a 95% likelihood of not getting a 7. Right? And the odds of not 7? How many ways can I not get a 7? 19. And how many ways can I not get a not 7? 1. Right? That's the number of ways I would fail at getting a not 7, is by getting a 7. A little bit double negative. I guess I could also write up here, if you want, odds of failure would just be F to S, I suppose, if you really want. Let's actually take a look at this. Notice that the odds of being 7, I said earlier, you could calculate odds by doing success, probability of success divided by probability of failure. If I did 1/20th divided by 19/20ths, I would still get the 1/19th, right? Or 1 to 19 ratio. So there's that. Let's talk about another example. So that's kind of the basic sort of idea behind probability and odds. Let's say I've got a brown paper bag, right? Here's my awesome brown paper bag. Right, here we go. So I've got a brown paper bag. In this brown paper bag, I've got, ready? 1, 2, 3, 4 yellow marbles. All right, this, I guess maybe you could just write this with words. 4 yellow marbles. Let's say I've got 1, 2, 3 red marbles. And let's suppose that I have 1 blue marble. Okay? So if I reach into this bag, all right, and just grab a single marble, assuming that all of these marbles are of equal size, and therefore if they were shaken up and I reach into this bag at random, all right, it's assuming all of them have an equally likely outcome of being selected. What is the probability that I select 1 yellow marble? Well, how many ways can I successfully get a yellow marble? There are 4 yellow marbles. Over the total, how many total marbles are there? 8. So 4/8 reduces to 1/2, or a 50% chance, right, that I'll get a yellow marble when I reach into the bag. Now, I actually can use our combinatorics abilities to count the number of successes and the number of total possible outcomes. Since I'm selecting 1 marble, I could have thought of this as the combo 4-1. How many ways could I pick 1 of those 4 marbles? Over the probability, or the number of ways I could have selected any marble. Well, there were 8 marbles. What's the probability, or the number of ways I could select 1? And the probability would have been the ratio of the number of ways I could select yellow over the number of ways I could select any marble, and this still ends up equaling 4/8 when I do that all out, or 1/2. So I just want to point out you can use your combinatorics to figure out the S and F if in fact it would be easier to do so. Let's see, what is the probability that I select, let's see, 2 yellow marbles if I'm pulling 2 out at a time? Let's see. Well, you could rely back on your basic counting principle concepts. The first selection I have, there are 4 yellow marbles to pick from, and then the second selection, you could kind of think that there are 3. However, let's do this using combinatorics. Of the 4 yellow marbles, how many do I want to pick? 2. And of the total number of marbles, 8, I want to find out how many ways could I have selected 2 of the 8, right? Any 2 of the 8. So for combo 4-2, let's see, that's going to be, well, 4 factorial up top, that'll come back to that. 4 minus 2 factorial is going to be 2 factorial, so 2 times 1 and 2 times 1. And up top 4 times 3 times 2 times 1 if you really want it. And this is all over combo 8-2, which is, well, in the denominator of this denominator, that's kind of weird, denominator, I'm going to have 8 minus 2 factorial, right? Which is 6 factorial. And then r factorial is 2 factorial, or 2 times 1. And then in the numerator, I'll just have 8 times 7 times 6 factorial. So I've got double combo problems going on here. But let's see what cancels out. So the 6 factorials in the denominator cancel out. The 2's in the numerator part cancel out. I could cancel out one of those 2's with a 4 partially and get a 2. I could cancel out a 2 in the denominator with the 8 in the denominator and get a 4. Let's see what we end up getting. So I'll have up top 2 times 3 is 6. Down bottom I have 4 times 7 is 28. And I think those reduce by 2 3/14 is the likelihood of that event occurring. All right, so I just want to point out that our combinatorics, the idea of counting the number of ways an event can occur, is going to be really helpful when doing probability, right? Because I count two things to do probability. I count the number of ways it successfully occurs and the total number of ways it could occur. So it actually would be quite handy to know that information. So let's do one more question based off of this setup. What is the probability of selecting one yellow and then one blue? So I'm selecting two altogether. So how many ways can I select a yellow marble? There are 4 to pick from, and I'm picking 1. And how many blue marbles would be left after selecting that yellow marble? Wait, how many blue marbles? There was 1. You're right. All right. You got me. I forgot how many blue ones there were. So I would be able to multiply those, right? Those individual numbers of events, and that would give me the total number of ways that could occur. And now in the denominator, how many marbles did I pick? 2 out of how many? 8. Okay, so this one's a little bit fancier, but it's actually not terrible. So let's see, up top, combo 4, 1. I think that ends up just equaling 4, if I'm not mistaken. Combo 1, 1, I think it ends up equaling just 1. And the 8 combo 2, we just did that work a little bit a moment ago, but 8 times 7 times 6 factorial over 6 factorial times 2. What was that going to be? 28, I think, when it all is said and done here. Wait a minute. Yep. So I'll get 4 out of 28, and then I can reduce that. Both of those are divisible by 4 to 1/7. All right, so it kind of works out, right? It's not too crazy. Now technically, I don't know if I want to jump the gun too much. Maybe this isn't. The same problem I could have set up as saying, okay, an alternate approach, but I definitely want you to use the combination approach. How many yellow could I have picked from for the first selection? There was 4. And how many marbles were there altogether to pick from? There was 8. And then for the second selection, I was picking 1 blue marble. Out of how many marbles? Well, there was only 7 left over. Let's see, is this going to work out? Let's see. 4 and 2. No. I'd have to actually multiply this by another piece in order to get this to work out right. Because I'd have 1/14 and I'd be small by too much. Because I think I'd have to consider that I could have selected the blue one and then the yellow one, or the yellow one then the blue one, which could have occurred in 2 ways. But nonetheless, I just want to point out that there is kind of a way you can set it up using some other approaches, but right now I'm definitely a fan of the combinations approach as much as possible, because knowing whether or not we would have needed that 2 kind of gets a little bit weird to have to rely on that. Okay, let's consider one more type of example for today. All right, let's say that you're in quality control, all right, and you're at a company that's manufacturing, I don't know, chairs, all right, and in a batch of 100 chairs, all right, let's say that there are, I don't know, 10 defective chairs. And I don't know if you determine that chairs are defective just by like maybe maybe you are a large person and you just sit on these chairs repeatedly to find out which ones are defective. Maybe you analyze the strength of the chairs using some sort of machinery. Maybe you analyze the assembly of the chair, just like the screws and how they were put together. I don't know. Who knows? Maybe they were painted the wrong color. Whatever. But they're defective. And in the factory, they don't actually want you to test every chair, because that would take you a long time. That would take them a lot of money. And they want to just like get these chairs out there, and they're just like, what the heck? We don't care if these chairs lose lives as a result. We want to make money, right? Maybe that's what they're saying. I don't think people die from chairs, do they? I hope not. Maybe wrestlers do when they're hit in the head with a chair. But anyways, so what you would do is you would select a portion of these chairs and test them. So this is the idea. What is the probability, all right, if you select 3 chairs at random? What is the probability that all 3 are defective? So probability of 3 out of 3 defects. So that's what we're trying to figure out. So how could we set this up? How many ways could I select 3 defective chairs? That in this case, selecting a defective chair is success to me. So once again, I just want to point out, success and failure are not your innate assumption of what is good and bad in the problem. All right, it's whatever the probability is asking. So I want to select 3 out of the defective chairs, so that's 3 out of 10 that I'd be doing as a combination. And we want to select, find out the total number of ways I could have just selected any old chair, right? So how many ways can I select 3 chairs out of the 100? And that would be our setup. So for the numerator, well, before I set up the numerator's numerator, I'll set up the numerator's denominator, however weird that is to say. I would have a 10 minus 3 or a 7 factorial. That looks like that's going to be the largest of those. So for the numerator, I should do 10 times 9 times 8 times 7 factorial. So this 7 factorial will preemptively be able to be canceled with that. Times 3 factorial. So that's 3 times 2. And for the denominator, right, the demondonator, like the big denominator, in its denominator, this guy, my own words, I'd have 100 minus 3 factorial or 97 factorial, right? And a 3 factorial, 3 times 2. So up top I'll have 100 times 99 times 98 times 97 factorial, right? So let's cancel out what we can. So the 7 factorials, the 97 factorials, 3 and 9 partially cancel, giving me 3. 2 and 8 partially cancel, giving me 4. In the denominator, 2 and 100 gives me 50, and 3 and 99 give me 33. So let's see, what we'd have is 10 times 3 times 4. 3 times 4 is 12, times 10 is 120. In the denominator, we'd have 50 times 33 times 98. And I get 1,61700. And it looks like that would reduce partially anyway. it reduces apparently to 2 out of 2695 when you divide that all out. Apparently 60 went into each of those. And that as a decimal is, let's see, 0.00074. So it's very unlikely you're actually going to select all 3 of them defective. All right, but you can kind of at least figure that out. So the point is selecting just 3 chairs, you're probably not going to find all of them. Some of these defective chairs are going to make it out to the public. Maybe your random selection should be more than 3, right? And you can kind of figure that out there. However, technically exposing those defective chairs would not happen, or finding out if there were any defective chairs would not happen if you only got 3 out of 3. Let's just do one quick analysis, quick setup of what if I wanted just at least, or exactly 1. Sorry, I won't use the word at least. Exactly 1 out of 3 defective. And this will be our last question. So, in order to figure this out, well, how many defective chairs are there? There are 10, and I want to pick how many of them? 1. Now I'm selecting 3 chairs altogether, so I wanted exactly 1 of these chairs to be defective, so that means I'm picking 2 other chairs. And what am I selecting those chairs from for this to be a success? There are 90 non-defective chairs that the other 2 would have had to be picked from. Okay? So that's kind of weird to think about, all right? Combo 10-1 is the number of ways I could have picked that 1 defective chair. Combo 92 is the number of ways to get the other 2 that are specifically not defective. And then I would put this over the denominator of combo, let's see, I'm picking 3 chairs all together out of 100. So let me actually do this up in a calculator real quick, so I won't do this by hand. Well, actually, combo 10-1 is easy. That's just 10. Combo 92. Let's see. So I do 90, math, go over to the PRB menu, go down to combo, and hit not 5, 2. And I get 4005. And then 100 combo 3 is the same denominator from earlier. So this would be 40050 over 161700, which I think I can reduce at least by 10. It reduces to 267 out of 1078. And that is a percent or decimal as 0.248, we'll call it. Or as a percent would be 24.8%. So using your random selection of 3, you've got a 25% chance almost of getting exactly 1 out of 3 defective. Now, tomorrow perhaps we'll consider asking the question of at least 1 out of 3 defective, which would require some additional work to figure that out. But this is the idea. Probability, number of successful ways an event can occur over the total number of ways an event can occur, and you can see why combinatorics and probability are such good friends. They get along, they help each other out. It's a wonderful thing. So have a great day, everybody. Bye-bye.